Somewhere beneath the North Atlantic, at a depth that no sunlight has ever reached, a vessel the length of a city block is moving at 25 knots. It has been underwater for 74 days. Its crew of 135 men have not seen the sky. They have not breathed unprocessed air. They have not stood on ground that does not vibrate with the low-frequency hum of a pressurized water reactor turning seawater into motion. And here is the question that almost no one stops to ask seriously. Where is the oxygen coming from? Not in the philosophical sense. In the precise, mechanical, molecular sense. Because the atmosphere inside that submarine is not natural. It is manufactured. Every breath that 135 men take, every hour of every day, for months at a time, is the product of an engineered system that has to work without failure, without interruption, and without a single point of collapse. This is not a story about nuclear propulsion. That part is well documented. This is the story of the engineering that keeps the crew alive while the reactor keeps the ship moving. The life support architecture of a nuclear submarine. The system that no one explains because it is not dramatic enough for headlines, and yet without it, every other system on the vessel is completely irrelevant. Start with the fundamental constraint. A sealed environment containing 135 human beings consuming oxygen and exhaling carbon dioxide will become lethal within hours if that exchange is not managed at a systems level. The human body consumes approximately 550 liters of oxygen per day at rest. Under physical exertion, that figure rises significantly. Across a crew of 135, you are managing an oxygen demand of roughly 74,000 liters per day, every day, for a patrol that can last 90 days or more. You cannot carry that volume. It is not physically possible to store enough compressed oxygen aboard a submarine to sustain a crew for a full deployment. The numbers simply do not work. The solution the United States Navy settled on, and which remains the primary oxygen generation method on every Los Angeles-class, Seawolf-class, and Virginia-class submarine currently in service, is electrolysis. The process is chemically straightforward. Pass an electrical current through water, and the molecular bond between hydrogen and oxygen breaks. Water, H2O, separates into its component gases. Hydrogen exits through one line. Oxygen is captured, filtered, and pumped into the vessel atmosphere. The system is called the electrolytic oxygen generator, and aboard a nuclear submarine, it is one of the most strategically important pieces of equipment on the vessel. Its power source is the reactor. The same reactor that drives the propulsion shaft generates the electricity that splits the water that produces the air. This is the closed loop that makes extended submergence possible. The reactor does not just move the ship. It sustains the crew. But oxygen generation solves only half the atmospheric problem. The other half is significantly more dangerous. Carbon dioxide is not a simple waste product to manage. At concentrations above 1% of the atmospheric mix, it begins to impair human cognitive function. Above 3%, crew members experience headaches, disorientation, and reduced decision-making capacity. Above 5%, it becomes acutely toxic. And in a sealed pressure vessel with no atmospheric exchange, CO2 concentration rises continuously with every breath the crew exhales. The primary system for managing this aboard U.S. Navy submarines is the monoethanolamine CO2 scrubber, commonly referred to as the MEA system. Monoethanolamine is an organic chemical compound with a specific molecular property that makes it useful here. It reacts readily and reversibly with carbon dioxide. When submarine atmosphere is passed through a solution of MEA and water, the CO2 bonds chemically with the MEA molecules and is removed from the airstream. The cleaned air is returned to the vessel atmosphere. The word reversible is important. When the MEA solution, now saturated with CO2, is heated, the bond breaks. The carbon dioxide releases, is captured, and is vented overboard through a specialized system. The MEA solution regenerates and returns to the absorption stage. The same chemical compound scrubs CO2 continuously, cycle after cycle, without being consumed. This is not a filter that needs replacing. It is a chemical engine running a continuous absorption and regeneration cycle, powered by waste heat from the reactor system. There is a backup system. Lithium hydroxide canisters, the same technology used in spacecraft, can absorb CO2 through a direct chemical reaction that produces lithium carbonate and water. These are consumed in the reaction and cannot be regenerated. They are reserve capacity, not primary infrastructure. Their presence aboard submarine vessels reflects a core engineering principle. Every critical life support function requires an independent redundant system that operates on a completely different mechanism. If the MEA system fails, you do not fix it and hope. You switch to a system that cannot fail in the same way because it operates on different chemistry entirely. Oxygen and carbon dioxide are the primary concerns, but they are not the only variables in the atmospheric equation. A submarine atmosphere also accumulates hydrogen, a byproduct of the electrolysis process and of battery charging operations. Hydrogen is flammable at concentrations above 4% in air. Managing hydrogen accumulation requires a catalytic burner system that combines the hydrogen with oxygen at a catalyst surface to produce water vapor, eliminating the gas before it reaches dangerous concentration. The atmosphere also accumulates trace contaminants. Lubricants, cleaning solvents, and materials off-gassing from equipment and hull insulation all introduce chemical compounds into a sealed environment that would disperse harmlessly outdoors but concentrate dangerously in an enclosed space over weeks and months. Activated carbon filtration systems run continuously, stripping these compounds from the atmospheric mix. The net result is an atmosphere that is not natural air. It is a precisely engineered gas mixture, continuously monitored by atmospheric analysis systems that track oxygen percentage, CO2 concentration, hydrogen levels, and trace contaminant presence in real time. The submarine's crew is breathing an atmosphere that is more carefully managed than the air in most hospital operating theaters. Now consider the structure that contains all of this. The pressure hull of a Virginia-class submarine is fabricated from Hy-100 steel, a high-yield alloy with a tensile strength of 100,000 pounds per square inch. At the vessel's operating depth, the external water pressure acting on the hull surface is approximately 600 pounds per square inch. The hull geometry, a circular cross-section, distributes this compressive load uniformly around the circumference, avoiding stress concentrations that would occur in flat or irregular surfaces. But pressure cycling creates fatigue. Every time the submarine dives and surfaces, the hull experiences a full compressive loading and unloading cycle. Over the service life of the vessel, these cycles accumulate. Material science tracks this through a concept called fatigue life, the number of stress cycles a material can endure before microscopic crack propagation begins to compromise structural integrity. This is why the service life of a submarine is not measured purely in years. It is measured in dive cycles. And it is why the inspection and maintenance regime for submarine pressure hulls is among the most rigorous in any engineering discipline. A crack that would be a maintenance issue in a surface vessel is a catastrophic failure event underwater. The nuclear submarine is typically discussed in the context of its weapons, its missiles, its reactor, its speed and depth capability. Those systems are the reason the vessel exists. But the reason the vessel can execute its mission for 90 days without surfacing is not the reactor. The reactor provides the power. The reason is the atmospheric engineering, the electrolysis systems, the CO2 scrubbers, the hydrogen burners, the filtration loops that take a sealed steel cylinder at crushing depth and maintain inside it an environment in which human beings can think, decide, and act with full cognitive capacity indefinitely. That is the engineering that makes every other system on the vessel relevant. Without it, you have a very expensive torpedo tube that kills its own crew. With it, you have the most strategically capable military platform ever constructed by human hands. That distinction is worth understanding precisely. Tactical ledger, the engineering behind the machine.